today's lecture, we will continue solving examples. So I will start by doing a DC shunt machine question. So we have a 240 volt DC shunt motor. So once we know that the motor is shunt, so we'll start by sketching the machine. So here we have a source DC battery, then we have our field circuit connected in parallel to the armature circuit, and in the armature circuit we have an armature back EMF. We have torque and speed out of the motor, I armature, R armature, RF, V source. So the currents we have now, we have I source, IF, and IA. So we start by sketching the circuit once we know that the circuit is DC shunt motor. And the motor is 240 volt, which means that this battery or the source here is 240 volt. And this source will be constant unless otherwise is mentioned in the problem. Now the motor takes an armature current of 20 amp. When the motor takes an armature current of 20 amp, so it is stated clearly that the current is armature current. So please don't go and say this is I source. So this is a common mistake that students will say I source equal to 20 amperes. This is not correct because it is stated that the current is armature current. This is one of the common mistakes that students do in this type of questions. Now we are given directly that the machine takes an armature current of 20 amperes. And the machine runs at 960 RPM. So we can write that the speed equal 960 RPM. The armature resistance is 0.2 ohm, so this resistance here is 0.2 ohm. Determine the no load speed. So the question is find no load speed. So you are given certain loading condition and you are asked to find the speed at the different loading conditions. So we can divide these into case 1 and case 2. So case 1 given IA given speed, and case 2 what we know about case 2 that it is only no load. So we need to find the no load speed. What is given at no load that the no load current is 1 ampere, and this is the no load armature current. So I armature in case 2 equal to 1 ampere. So let's name this case as case 1 and let's name this case as case 2. So the unknown will be what is the second speed in 2. And as we mentioned in our previous lecture, that whenever you are asked about speed, you have to think about E. So this question is simply calculate EA2. So in DC machine problems, try to have like a reference state or reference case. Reference state or reference case means a case where you know every single variable, and the variables are EA, IA, IF, speed, T developed. So if you know all these variables, this is a complete state or complete case that you can use it as a reference case. So let's start by case 1 and calculate what is missing. So for case 1, we know that EA1 equal to V source minus RA IA1. This equation is simply KVL. So given the values in the question, so V source is 240, RA is 0.2, IA is 20. This will give us 236 volt. So now we know that EA1 equal 236 volt. And we have IA1 as 20 amp. And we have speed 1 as 960 RPM. These are the data given. Now can we calculate I field? For case 1, to calculate I field, it's a V field over R field. We know that V field equal V source because we have a shunt machine, so the voltage across the field here is the same as the voltage of the source. So we know that V field is V source divided by RF. So this current is 240 divided by RF, but we don't have RF. So let's see, do we need actually to calculate this current or not? Now, let's go to case 2. Let's add a page first, and let's go to case 2. So for case 2, what we know that the armature current goes down to 1 ampere. So we can calculate E armature 2 as V source minus RA I armature 2. As you can see here, I used the V source without any subscript as 2 or 1, because the voltage of the source will be assumed constant unless it's stated otherwise. So here equal to 240 minus 0.2 multiplied by 1 equal 239.8 volt. So now we know that E armature 2 equal 239.8 volt. Now can we calculate I field in this case, case 2? So I field will be V source divided by RF. V source is 240 and RF is unknown. As you can see, this value is exactly the same value for I field of the first case. So I field 1. So as we can see here, for shunt machine, when V source is constant and RF is constant, IF will be constant. And this is a rule for shunt machine. So for shunt machine, the only exchange that you will see in the field, only the field current will change if V source is changing or RF is changing. As in this example, neither V source was changed nor RF was changed, so we can say that IF is constant. Given this, we can say, okay, EA equal to K motor IF speed. So we can apply this equation at the two states. So we can say EA in case 1 divided by EA in case 2 equal I field 1 divided by I field 2 multiplied by omega 1 divided by omega 2. So for the ratio between the speeds, doesn't matter what is the unit. Already you are dividing omega 1 by omega 2. So if omega 1 is radian per second and omega 2 is radian per second, or the speed in RPM, the second one has to be RPM. So we can write this equation as IF1 divided by IF2 N1 over N2. So we can write it as RPM ratio or radian per second ratio, given that the two speeds have the same unit, because we need the ratio. And as we said that I field 1 over I field 2 is 1, because the field is constant, so we can say that EA1 divided by EA2 equals to N1 divided by N2. So EA for case 1 was 236 and the speed was 960. EA for case 2 is 239.2. N2 is unknown. So from this equation, we can get that N2 equal to 975.45 RPM. So as you can see here, when the motor goes to no load, the speed goes from 960 to 975 RPM. So at full load, the machine was running at 960 RPM. Then at no load, when you totally remove the load, the machine speed jumps to 975.45 RPM. So as you can see, when you remove the load from the machine, its speed goes up. And you can see here for shunt machine that the change in the speed is not large. The change or the machine speed changed only from 960 to 975.45. So if we take the ratio, which is 960 negative 975.45 and divided by 960, this will give us what is called a speed regulation. So if we take the no load speed minus the full load speed divided the full load speed, so 975.45 minus 960 divided by 960 multiplied by 100%. So this machine regulation is 1.6%. This means the machine speed will change by 1.6% between no load and full load. And now we can write down this important claim. So let's go to the next page to see a comparison between shunt and series machine and write down this claim. Now I need to compare between two examples we did. So the first example we did was a shunt machine, which we just did now. For the shunt machine at no load, the machine speed is 975, and at full load the machine speed was 960. And I need to compare this with the series machine we did last time. So for the series machine, the machine at no load was or at full load was running at 600 RPM, while this machine, when the load is removed, the speed jumped to 25k RPM. Now, so let's write down this. For shunt machine, full load, the speed was 960 RPM. No load, the speed is 975.45 RPM. For series machine, for full load, the speed was 600 RPM. At no load, the machine speed jumped to 25,130.8 RPM. Now you can see how the shunt machine has very good speed regulation compared to series machine, and this is one of the main characteristics for each machine, which will give each machine a different application from the other machine. So for shunt machine, we can say this machine almost has constant speed. So if we need to sketch the relation between speed and loading, the difference between no load speed and full load speed is not too much. But if we need to sketch the torque speed loading or the speed loading characteristic for series machine, at no load the speed can go to infinity, and with loading this speed drops so fast. So these are the two main features of shunt machine and series machine, and we will go back to these two machines again when we study the torque speed characteristic, and we will explain in details why this characteristic look like this. So this machine has a very good speed regulation, and this machine has bad speed regulation. So now we are comparing between the two numerical examples we did for series machine and for shunt machine in terms of its no load speed. Now let's go to another problem here. So in this question here we have a 240 DC shunt motor, and this motor draws a line current of 173. So we mentioned before that I line is the source current going into the machine is 173 ampere, and this machine has a source voltage of 240 volt. So we can start by sketching the machine circuit. So here we have our source, the field is connected in parallel to the armature. Here we have EA, here we have our torque and speed, here we have our RA, our RF, our V source, and the currents are I source, IF, IA. So in any DC machine problem, please start by sketching the equivalent circuit. Now this machine runs at 650 RPM, so the speed equal to 650 RPM. The motor has an armature resistance of 0.00705 ohms and has a field resistance of 81.63 ohms. So the resistances values are given. The first question here is sketch the equivalent circuit. So whether we are asking you to sketch the equivalent circuit or not, you have to sketch the equivalent circuit. The second part is determine the motor efficiency if the rotational losses are 732 watt. So if we sketch the power flow diagram, we have an input power, we have an output power, then between the input power and the output power, we have the field losses, we have the armature losses, and we have the mechanical losses. The mechanical losses are given as 732 watts, and this value will be constant. So you have to consider the mechanical losses as a constant value. So this value is constant. So whatever a mechanical losses is given, this mechanical losses given will be constant for the whole question. So to get the efficiency, we need to find our P out and we need to find our Pn, then we need to divide P out by Pn. So the simple part here that we can calculate is Pn, because Pn is V source I source. So we can start by saying that the input power equal to V source I source equal to 240 multiplied by 173. So we can calculate this value. So we can start by calculating what is the input power, because calculating the input power will need no calculation, no other calculation, because it's simply V source I source. Now to get the output power, we need to subtract these losses from the input power to get the output power, or we can do a jump. We can start at this point. So if we start at this point and then we proceed forward, we can get the output power as this power subtracted minus the mechanical losses. So what is the power at this point? So the power at this point is simply the developed power EAIA. So the idea here to get the output power is to calculate the developed power. So we need to calculate EAIA. And to get EAIA, we will start by calculating IA. So we are given that I source equal 173 ampere, which equals to I field plus IA. This is one equation in two unknowns. We don't know what is IA, we don't know what is IF. But we know that V source equal to VF equal to RFIF. So we can calculate IF as V source over RF, which will equal to 3 amperes. Now from 1, we can now say that IA equal to 170 amperes. So we have IA as 170 amperes. Now let's add a new page. Now we have IA as 170 amperes. We can calculate EA as V source minus RA IA, which is KVL in the armature circuit. So V source is 240 minus RA is 0.0705 multiplied by IA is 170 amperes. So we can calculate EA to be 228 volt. Once we have EA and we have IA, we can say, okay, P output equal to P developed minus P mechanical losses equal to EA IA minus P mechanical losses. So EA is 228, IA is 170, minus the mechanical losses is 732 watts. So we can calculate our P output in this case. So P output equal to 38,028 watt. So this is the output power from the machine. So the output power is the net power, is the shaft power, is the load power. So this is the developed power after subtracting the mechanical losses from this power. Now we can calculate the efficiency as P out over Pn, and to get a percentage, you will multiply by 100%. So this equal to 38028 divided by 41520 multiplied by 100%. So the percentage efficiency equals to 91.59%. And we need to keep this value in mind when we move to another motors like synchronous and induction machine. And as you can see that the DC machine is an efficient machine. The efficiency is 90 plus. So now we are done with the first part, which is finding the efficiency. So whenever you are asked to find the efficiency, you need to go through the power flow diagram. And you can jump in the power flow diagram by starting at the developed power and then subtracting the mechanical losses. Now you have your P output. Now what if you are asked to calculate the output torque? So the output torque is simply P out divided by speed. So P out is 38028 divided by the machine speed is 2 pi over 60 multiplied by 650, which is given in the question. So we can calculate the machine torque or the machine output torque at this stage. So 2 pi divided by 60 multiplied by 650, and we should divide the power by this value. So this will give us 558.67 Newton meter. So we can calculate the output power or the output torque because the output power is T output omega. So don't forget that the developed power is T developed omega. So if we compare these two together, so the speed is the same as the speed. So speed is the same as speed, but T output is less than T developed due to losses. So T output is less than T developed due to mechanical losses. Now let's go back to our question here. Now this is a typical part of the style of the exams in DC machines. So after you are given a full case scenario, which is the case here, you will be given a case with some unknowns. So here we are saying that there is a reduction in load. So part of the load was reduced. And due to the reduction of the load, the armature current dropped to 70% of its value. Again, that the armature current dropped, not the machine current or the motor current, the armature current. And the terminal voltage is unchanged. The terminal voltage V source is unchanged. And this is your regular assumption. So if this part is given or this statement is given or not, this is what you should assume. So you should assume that the terminal voltage will stay the same and the terminal voltage will not change unless it is stated clearly that the voltage was changed. Now we need to define the new case. So let's add the page here and define the new case. So for the new case, let's name it as case 2. So the load dropped to 70% of its value, which made our I armature 2 70% from our I armature 1. So we can calculate our I armature 2 as 0.7 multiplied by the value we have for I armature 1, and the value we have for I armature 1 is 170. And this is one of the mistakes that some students do, that they assume that the reduction happened in the line current, but it is stated in the problem that the reduction happened in the armature current. So I armature 2 equals to 0.7 multiplied by 170 equal to 119 ampere. So the armature current dropped to 119 ampere. And as we mentioned in lectures, that the machine current is like your car gas. If the load on your car going down, so the gas consumption will go down. So if you throw part of the load of the machine, of the motor, the gas going into the motor or the current going into the motor will be less, and the armature current will be less. Now in case 2, we have I armature 2 equal 119 ampere, but it is stated in the question that the source voltage was unchanged, and also RF is unchanged. Nothing is stated in the problem about it changing RF. So given this, we can write down that I field 2 equal I field 1. No change in I field equal to 3 ampere. So we can say that the field current will remain the same. Now let's go to see what is required. So what is required here is calculate the new line current. What is the line current or the source current in case 2? So to get the new line current, so I source 2 is I field 2 plus I armature 2. I field 2 is 3 ampere, I armature 2 is 119. This will give us 122 amperes. So now we have the second source current or I line 2. So the second line current of the machine is 122 amperes. Let's go back. Calculate the new motor speed. Now, now we need to calculate speed 2. And as we mentioned early, that when we are asked about speed, you have to think about EMF. So we need to calculate what is E armature 2. To calculate E armature 2, we have only one equation, is V source minus RA IA2. It's only KVL. So V source is 240 minus RA is 0.0705 and IA2 is 119. The only unknown in this equation is E armature 2. So E armature 2 is 231.6105 volt. This is our second EMF. The EMF in case 2 is 231.7. Compare this value to 228 volt EA1. As you can see, there is a jump in EA. And why there is a jump in EA? Because the speed will go up. And why the speed will go up? Because you removed part of your load. Whenever you reduce the load on your machine, the speed will go up. So think about your car if you are going downhill. So now you remove the part of the load. So what will happen? Your car will accelerate. Your speed will go up. But if your car is going uphill, your speed will decrease because you are putting or throwing more load on your engine or your machine. Now the question was not to calculate EA2, but the question was to calculate the second speed, N2. So how we will calculate N2? We will do the same as we did in the previous questions, that EA1 divided by EA2 equals to IF1 divided by IF2 multiplied by N1 divided by N2. And as we mentioned, that IF1 over IF2 equal 1 because we didn't change the source and we didn't change the field resistance. So we can say that 228 divided by 231.61 equal to N2 is unknown and N1 is 650. So the only unknown in this equation is N2, which is 660.293 RPM. So as you can see, this is the speed when your current dropped to 70% of its value. This means you reduced your load by 30%. And when you reduced your load by 30%, your speed went up by just 10 RPM out of 600. That's why, again, we can assume this machine, the shunt machine, as a constant speed machine. So I will use M/C for machine. So the shunt machine is a constant speed machine. And this is one of the applications for the machine. So whenever you are looking for a motor that can give you a constant speed, regardless of your load, your champ is shunt machine. So what is an example for this? Assume you have an elevator, and this elevator is connected to a motor. If this motor speed it change with the load, so whenever there is more people inside the elevator, the motor speed will go down, and the elevator will take different time to go between floors. So in order to have the time between floors to be independent from the number of people riding the elevator, which represents the load inside the elevator, we need a motor here with constant speed, which means the motor torque, not the motor torque, the motor speed will not change by decreasing or increasing the load. So if we have 4 persons inside the elevator and one get out from the elevator, the speed will not jump and you will go faster. This will not happen if your machine has a constant speed. And at that time, they used DC shunt machine for this motor. So this is one application for DC shunt motor is elevators. And why they use DC shunt motors for elevators? Because DC shunt motors offers you a constant speed regardless of your load. Also another application for DC shunt machine is conveyor belts. So if you have a motor and this motor is running a conveyor belt and you are putting boxes on these conveyor belts, you need the conveyor belt to go with constant speed regardless of how many boxes you have. If you have one box, two boxes, or whatever the number of boxes, you need your production line to go at constant speed. So the champ here, or the best motor here to use, is shunt motor again. Why we will use shunt motor? Because it offers constant speed while your load is changing. Your load here means what is the load you put into the motor, how many boxes it is driving in the conveyor belt, or how many persons are riding the elevator. And we will come back to this characteristic again when we study torque speed characteristic. Now let's go back to the problem here. Now we need to find the motor output torque assuming that the mechanical losses remains constant. Okay, if it is mentioned or not, the mechanical losses will be always assumed constant. So we need to calculate what is the new output power. So to calculate the new output power, we will say, okay, P output 2 equal to P developed 2 minus P mechanical losses. As you can see, we gave subscript 2 for P developed because P developed will change, but the mechanical losses is constant, so we will not give it a subscript 1 or 2. So P output 2 will be E armature 2, I armature 2, minus the mechanical losses is 732. So EA2, we found EA2 to be 231.61, and I armature 2 is 119, negative 732. So we can get P output 2. So P output 2 is 26829.65 watt. So we can get the second output power. Now, what if we needed to calculate the second efficiency, the second percentage efficiency? So to calculate the second percentage efficiency, we will use this power 26829.65, and we will divide it by 240 multiplied by the second line current, which was 122. Now let's calculate the second efficiency. So the efficiency of the machine is 91.6%. And as you can see that the machine efficiency is changing with loading, and you removed 30% from your load, and still your efficiency is 90%. And this is one of the main advantages of DC machine. That's why DC machines are still used in robotics. These machines are powerful machines and they have high efficiency.